Module Technical Course Additive Manufacturing for Industry 4.0. Lecture 2 Technologies of Additive Manufacturing. During this lecture, we will discuss techniques, materials, equipment, as well as advantages and challenges of additive manufacturing. The International Organization for Standardization and the American Society for Testing and Materials classify additive manufacturing techniques into 7 categories as wet photopolymerization, material jetting, binder jetting, material extrusion, powder bed fusion, sheet lamination, and directed energy deposition. When choosing a particular technique, a compromise must be found between process speed, volume, and tolerances. For these additive manufacturing techniques, various technologies have been developed in response to industrial demand, most of which are based on the method of layer-by-layer material deposition. The major differences between the techniques include the raw materials used, the states of the material, and the adhesion between the particles of the material. For example, for production of functional structural parts, such technologies are often used as fused deposition modeling, selective laser sintering, electron beam melting. For non-functional structural parts, such technologies are often used as stereolithography that can provide application of resins for smoothest surface that is good for casting, or 3D printing with plaster or sand for marketing and concept prototypes, as well as sand casting molds. Process equipment applies successive layer of liquid, powder, paper, or sheet material, building a three-dimensional model from a series of cross-sections. Some additive manufacturing techniques provide the use of multiple materials, as well as different colors within a single production run. For example, it is possible to print a model from one material with supports printed from another, easily soluble material, which makes it easy to remove support structures after the printing process is completed. More detailed information about modern techniques, materials, and current advanced in additive manufacturing you can find in these papers. Metal additive manufacturing is a fast-growing part of 3D printing. Let's watch this video illustrating direct metal laser sintering technology as an example.
Direct metal laser sintering, also known as DMLS, is an additive manufacturing technology that creates metal parts directly from 3D CAD data without the need for tooling. DMLS utilizes a variety of metal and alloy materials, such as stainless steel, cobalt chrome, and Inconel, to create strong, durable parts and prototypes. DMLS is an excellent choice for functional metal prototypes, high-temperature applications, and end-use parts. The DMLS process begins in the same fashion as other layer additive manufacturing technologies. A program takes 3D CAD data and mathematically slices it into 2D cross-sections. Each of these sections will act as a blueprint, telling the DMLS machine exactly where to sinter the metal material. The data is then transferred to the DMLS equipment. A recoater assembly pushes powdered metal material from the powder supply to create a uniform layer over the base plate. A laser then draws a 2D cross-section on the surface of the build material, heating and fusing the material. Once a single layer is complete, the base plate is lowered just enough to make room for the next layer. More material is raised from the cartridge and recoated evenly upon the previously sintered layer. The DMLS machine continues to sinter layer upon layer, building from the bottom up. As the part is built, support structures are added to give supplemental strength to fine features and overhanging surfaces. The completed part is then removed from the base plate and are treated with an age-hardening heat process to further harden the part. Any support structures are also removed at this time. With numerous surface treatment and hand polishing options available through service providers such as Solid Concepts, DMLS parts can be used in highly cosmetic applications. Typical uses for DMLS include tools and manufacturing aids, small integrated structures, dental components, surgical implants, and aerospace parts.
For additive manufacturing, both industrial professional 3D printers and desktop ones are used. Professional 3D printers allow to print from a wide range of materials from full color, plaster to steel. Almost every material uses its own 3D printer and 3D printing technology. The key points when choosing the right equipment for additive manufacturing are the speed of printing, the price of a 3D printer, the cost and range of compatible consumables, and as a result, the cost of products. Desktop 3D printer consists of a body, guides fixed on it, along which the print head moves with the help of stepper motors, a desktop on which the product is grown, and all this is controlled by electronics and special software. Desktop 3D printers mainly create three-dimensional objects using the fused deposition modeling method. Thermoplastics such as ABS or PLA plastics are used as 3D printing material. Consumer 3D printers are well suited for printing 3D models with simple geometry where increased accuracy is not required and the presence of visible layers of printing is not critical. Let's watch this video illustrating 3D printing process with our 3D printer Leapfrog Creator as an example. Different materials are used in additive manufacturing. The main groups are thermoplastics, thermosets, powder-based composites, metals, paper, sand. The list of materials for additive manufacturing is constantly expanding. These videos demonstrate the use of carbon material and wood chips for 3D printing. Carbon fiber can be made to be stronger than many metals and is often a top choice when strength is a requirement. However, not all carbon fiber can be classified as stronger than titanium. 3D printers are not just for printing metal and plastic. You can also use them to print woodwork projects. In this case, it is possible to create programmable structures that take their shape under the influence of external factors, such as moisture. The main advantages of additive manufacturing are freedom from manufacturing constraints, instant assemblies, mass customization, freedom of design. The main challenge of additive manufacturing are most additive manufacturing processes introduce anisotropy in mechanical properties. Local differences in laser power introduce heterogeneity in mechanical properties. Laser fluctuations might result in embedded defects that are difficult to identify. All existing machines are open loop. Temperature sensors have been introduced in some processes, but the readings are not used to optimize the processing parameters on the fly. So, Despite the advantages in additive manufacturing, especially in the previous decade, and its adoption in engineering, design, and education, the process is far from being perfect, and some challenges remain. Therefore, additive manufacturing has not been heavily adopted in industries for fabricating the pieces used in final products. Consequently, 3D printer developers, industry, and academia have been studying additive manufacturing systems to reduce the possibility of mistakes and improve their overall reliability. The vast majority of additive manufacturing processes are still based on open-loop control or implement some local controllers for specific variables, such as temperature, making them susceptible for errors. Therefore, the task of improving control system for additive manufacturing as well as expanding areas of application remains relevant. On this slide, you can see recommended sources of information. Thank you for your attention.